So hello and welcome, guys. The reminders for today are that, first of all, our final exam is coming up on May 4th. That's a Monday at 9 a.m. So make sure you have the final exam on the calendar. Next of all is we have our usual quiz on Wednesday. It's going to cover sections 4.2 through 4.3, or at least whatever we get up through today. And then there will be the usual homework due on Wednesday. Okay, so before we get started, do you guys have any questions you'd like me to answer? All right. Well, the topic for today is section 4.3, which we're finally getting to the thing called the fundamental theorem of calculus, right? We've been kind of working up to this for a long time now. And essentially what it does is it relates derivatives and integrals. It tells us how the two operations are related. And so, the reason we started everything in chapter 4 with all those rectangles and areas and stuff, sort of the reason we did all that was we want, a way to find antiderivatives and understand what they mean sort of graphically. Yeah, and that's going to have something to do with integrals. An antiderivative isn't exactly the same as a definite integral. But let's sort of think about this. So the first idea we need to remember, because we're trying to create an antiderivative, sort of the simplest function you could take the antiderivative of is it would be a constant function. H of x is equal to some constant c. And the antiderivative of that, well, the antiderivative of a constant we've learned by now, I'll call that capital H for the antiderivative version. It would be just that c times x plus possibly another constant, right? Okay, so that means, a constant function is like a horizontal flat line. And that means its antiderivative is a slanted line, right? And it's, maybe it'll help if I put some references in here. So this would be h of x. If I draw the sort of corresponding version for the antiderivative, it's going to be some slanted line. And the important thing is that it'll have slope equal to c, right? So it turns a horizontal line into a sloped line with slope c. Okay, so that's sort of the key observation that kind of everything hinges on. And so the idea to take an antiderivative of a general function, it's of course more complicated. But what you do in general is, let's say we have some function f of x. And we want, so let's, what's the best way to put this? Let's imagine that this is the derivative of something. Okay. So this is the function, and we'd like to find the antiderivative, or what the original just capital F is. And essentially, the idea behind the fundamental theorem of calculus is you do this sort of rectangle idea where you chop your x-axis into little bits, and then on each bit, you approximate the function by a constant, right? So we don't actually need to draw the rectangles, right? Really what we're doing is we're, approximating the function as just little constants, right? Just a bunch of little constant functions, right? And so if we think about, if we sort of delete the red line, we'd just be left with a bunch of little horizontal bars, right? And these are all little bits of horizontal functions, and those we know how to take the antiderivative of, right? That's essentially what we did up here, is we know how to take the antiderivative of those individually. So when you do that, what happens is, you take the height of the first one. So one thing we know about antiderivatives is we don't know where to start, right? When we take an antiderivative, it could be shifted up or down by a constant. So we actually have to choose, let's give these a name. Let's call this the letter A. So A will come down here. And so we have to choose a starting point. Like we don't know, without more information, we wouldn't know where to start. So I'm just going to choose to start anywhere. And then what happens is, to get the antiderivative, this has slope equal to C1, right? Where C1 was this number. And then you do that on the next little interval, right? So then you have some next little bit. So, and then you have a next little height up here, C2. So the antiderivative of C2 is another line with another slope. Looks like it's a little bit higher slope. So that would mean your function goes up a little bit more, your antiderivative. Right, and then you keep going, right? You would have a C3. You'd have another portion of this line with an even slightly larger slope, right? And you could keep doing this forever. You don't know, but that's the main idea. So this is a way to sort of reconstruct the antiderivative as a bunch of little line segments, right? But if you take the line segments to be really small, like these little, if you make these really small, right? If you did a million little divisions here and you did this again, it starts to get more and more accurate. It's just like when we took rectangles and we used more rectangles, it got more accurate. It's the same idea here. Actually, it's exactly the same, just in different language. So the other thing to point out is, let me draw like just one of these little intervals. Not that one. So if I just look at the part from A to the A to A plus delta x, say, that was at a constant at a height of C1, right? So basically I'm just blowing up this little part. So you have this little constant function, and the idea is if you now map it downwards to what we were doing before, it just corresponds to this first little red line, right? You have some starting point at A, then it goes up a bit, to A plus delta x. And if we look at this little triangle here, okay, so how is it related to what we started with? So up top, this area, when we were doing all the rectangle stuff, was the width, which is delta x, times c1, or the height of the function, right? You know, a lot of times we did like right endpoints or something to find c1. Okay, now if you look at the length of this right-hand side, well, remember this red line has what slope? It has slope c1. And so if you have a line with slope c1 and you go from A to A plus delta x, that's a distance of delta x. So if you go over to the right by delta x, the line will go up by a amount exactly equal to delta x times c1. So it's saying the area in one of these little rectangles goes to the what we'll call the net change, or how much the function rose, right? So the function went up from, you know, whatever this height is to whatever this height. And that net rise, that net change, is exactly the same as the area under the original. Okay, so that's sort of the moral of the story here is this is the reason why antiderivatives are related to areas, is because, you know, if you do these little approximations, then the areas are exactly equal to the rise in the function, and if you just make it small enough, you get it exactly correct. So that's sort of the story behind the fundamental theorem of calculus. I'm not going to make you sit through the proof, so I feel like most of you would not be interested in that. So let me just tell you the moral of the story now is this theorem. Well, first maybe let me put all these pictures into words. What we just said is that the area under the derivative, the area under the derivative, say over some interval, is the same as the net rise, where usually we use the word change because it could be positive or negative if the area is positive or negative. In the antiderivative, the capital F. So if you calculate an area under a function, it tells you how much the antiderivative increased by or decreased if it was negative. Okay, so that's sort of what this picture was trying to tell you. And the details are quite involved. If you want to actually wade through the proof, it's in one of the videos I posted. But yeah, here's the technical version of the fundamental theorem of calculus. So it says if we have a continuous function on an interval, it turns out it doesn't actually have to be continuous, but that's the version we're going to stick to. It holds more generally. Then we can say two things. So part one, there's sort of two important parts to this, says that if I do a definite integral from a number, let me write it like this. I always debate which way to write this. Let's just stick to this way. So if I take the integral of my function from a to a variable x, okay? So this thing, it's important to realize this is a function of x, right? Because it says take the area under f between a and x, and I can move x, right? It's sort of like if I have a here and my function is somewhere up here, maybe we shouldn't always draw them above the x-axis. It could be down here or something. Or we could even make it something like this. It's a little awkward. Okay, say something like this, and then say b is here. I guess we don't have a b. But what I'm trying to say is this quantity up here depends on which number x you plug in. So if I plug in like one number for x, then I'll get sort of this area, right? If I move my x to the right, pick a different x, then I get more area, right? So it depends on x, right? It's sort of asking you to calculate the area from a to x, right? Which depends on x. I can plug different x's in. So that's why this thing is a function of x. And what we want to say about that is that this is an antiderivative. It's not the only one, but it's one of them. Right? Remember, there's multiple possible antiderivatives of just little f. So the point is, if you have a constant on the bottom, so down here, and a x on the top, then that's one way to calculate the antiderivative. Okay. So in addition to this, not only is it an antiderivative, this antiderivative is guaranteed to be continuous on the same interval and differentiable on the interior. But we're not going to worry too much about that. The main thing is that this thing is an antiderivative. Okay, so that's part one of the fundamental theorem of calculus. It says that definite integrals are one way of calculating an antiderivative. And how did I spell antiderivative so weird? Antiderivative. Okay, so then the second part is something that's very convenient for calculating. It essentially says that if I don't have any variables in my bounds, then one way to calculate this area is to just figure out the antiderivative. So it's sort of an opposite. You're sort of saying an opposite thing. But this part is exactly what I was making a picture of above, right? So when we went up here, we said the area under, the area under something is equal to the net change in the antiderivative. Capital F of. So that's exactly what this is saying. This is saying this right-hand side is the area, or sorry, the left-hand side is the area. This is the area. And this part here is the net change. But this one is actually really useful because we sort of know how to take at least a good bit of antiderivatives, right? We know how to do like x to powers, sines and cosines, cosecants, and that sort of thing. Or I guess cosecant squared. So yeah, so this one is more of like a calculating thing. Okay, so this is the fundamental theorem of calculus. We have, I usually sort of think, I usually remember the second one actually first. I don't know why. It says to calculate an indefinite integral, you find an antiderivative, capital F, and then you plug in the top minus plugging in the bottom. And then the other one, sort of a better, or another way of phrasing it at least is, so another way of phrasing part one is if you take the derivative of an antiderivative, so this thing is an antiderivative of little f, and we used, it may seem a little confusing why I'm using like t's in here instead of x's, and the reason is because we're using x here as sort of the end point of the area, and so we don't want to get confused about the t's when we start plugging things in. So it's just conventional that you keep those variables different. You didn't have to use t here. You could have used like z or u. But yeah, so what I was saying is, this part in here is an antiderivative of little f. So if I take the derivative of an antiderivative, well, those sort of undo each other, right? Because the antiderivative is something whose derivative is the original thing, right? So this all says that if you take the derivative of an integral when you have x as the upper bound, you just end up with the part inside, right? And here we write x instead of t just for sort of to make the notation make sense. Okay, so any questions about this so far? It'll probably make more sense when I start doing examples. So part 2 tends to be the part that gets used the most often, so I'm going to do that part first. So here's an example. And so let's use FTC to compute this integral. Okay, and if you think about that here, so if you think about number 2, it says to compute this integral on the left-hand side, we first have to find an antiderivative of whatever's inside here. So we first find an antiderivative of the inside. So we find an antiderivative, and that is something we should be able to do. Okay, so that will be, you increase the power by 1, divide by the new power, and minus 3x. And here, you don't need to put the plus c unless you really want to, because this says you can use any antiderivative you want. You can, so you can choose c to be 0. Or you can keep the plus c in there, and you'll see that they always cancel out. Okay, so then what you do is you take that, and you have to plug in the upper endpoint, the b, minus plugging in the a. And so there's sort of a standard notation that I should mention. When you write something like this is called evaluation. So sometimes they're also written as just straight lines. Sometimes you'll also see them as just from A to B without the little bracket. But either way, when you do that, it stands for an evaluation bar, and what that means is you take whatever's inside or to the left of it, and you plug in the top thing. Okay, so here let's put our actual numbers, 3 to 5. So you'll plug in 3 for x, and then you'll do the same with sorry, I said top number first, and then I write the other one. 3 times 5. And then you plug in the bottom number, 3. Right, so the 5 went in here, then the 3 is going to go in the next one. 3 to the 4th over 4. Okay, so you would get something like this. And so yeah, this is just the answer. I mean, you can simplify this if you want, of course, but they're rather large numbers, right? 5 cubed is 125. You're going to get up into the thousands here probably. But yeah, so that's the idea. Is so to compute an integral, what you do is you first find an antiderivative, then you plug in the top number, have that as a term, and then you subtract, plugging in the bottom term, making sure you subtract off the whole thing, right? So parentheses are important in the second term. Okay. So if we do another one of these, let's compute the integral from 0 to pi of sine of x plus cosine of x over 2. So why don't you guys take a minute and try this one? And then I'll tell you the answer. So take a minute and try this one. Okay. So to do this one, we first figure out an antiderivative of the interior. So the antiderivative of sine is negative cosine. And then we can think of the second one as just being a half cosine of x. So its antiderivative is 1/2 sine of x. And then we have to plug in from 0 to pi. And so so the first term will come in from plugging the top one. It always goes top first. So cosine of pi plus 1/2 sine of pi minus the second term where we plug in 0. One-half sine of 0. And that is something we can figure out fairly easily. So let's see, cosine of pi is -1, so we get minus -1, sine of pi is 0, cosine of 0 is 1, sine of 0 is also 0. Let's match our brackets. So we get 1 plus 1 is 2. So that integral, so this means that the area under this sine plus cosine over 2 function between 0 and pi is actually just the number 2, right? So as long as the function's, not super difficult, we can calculate areas just by, sort of figuring out the antiderivative. And that's one of the main powerful parts of the fundamental theorem of calculus. It says that, areas can be computed by finding antiderivatives. Okay. Let's do one more. Okay, so sorry, I meant secant squared, because we don't, secant cubed would be much harder to find the antiderivative of. So this one, again, you have to think like, what's the antiderivative of secant squared? So what thing has secant squared as its derivative? And if you think about it, that's just a tangent. So you end up with the antiderivative is 3 tangent of theta. And then we're going to evaluate that from pi over 4 to pi over 3. Right, so this is, sort of the other way of drawing that evaluation bar. But what it always means is it means plug in the top one minus plug in pi over 4. It's just sort of a convenient shorthand to keep track of that information. And so we do that. So we get 3 tangent of pi over 3 minus 3 tangent of pi over 4. So yeah, so 3, tangent is sine over cosine. So you could think about it, sine of pi over 3 is root 3 over 2 over cosine is 1/2. And then for pi over 4, sine and cosine are the same. So you'll see that, it's the same. It's like root 2 over 2 over root 2 over 2. So you end up with a 1. And so all told, this is 3 root 2 minus 3 if you do the fractions. Okay. So any questions about this stuff so far? It's somewhat straightforward once you get the notation under control. Maybe a comment is, what if I had these bounds switched? Because pi over 3 is the bigger one, right? So if I switch the bounds, we would expect, from what we talked about last time, we would expect to get minus the original, right? Right, that was one of the rules we learned last time, is whenever you switch the bounds on the top and bottom, you add an extra negative. But it turns out like you don't have to do that. You can just, you don't ever have to worry about the order of the bounds, even if they're in the wrong order. Even if like the top one is smaller than the big one, it'll still work out, right? You'll just end up with 3 tangent of theta from pi over 3 to pi over 4. And that'll be exactly the opposite here. You'll end up with 3 minus 3 root 2, which is negative of 3 root 2 minus 3. So it's exactly the negative of what we got before. So I just wanted to comment that, you don't have to worry about switching the bounds when you're doing a definite integral. They sort of take care of themselves with the evaluation. Okay. All right, so questions about, so this is how we're pretty much always going to compute antiderivatives from now on. Or sorry, this is how we're going to compute definite integrals, is by using antiderivatives. And once you get into more complicated functions, it can get a lot more tricky. We're going to do a little bit of that in a couple sections called U substitution, which is essentially the inverse chain rule. But there's there's like 100 different techniques you could, in principle, learn to do these things. So it's sort of more involved than just taking derivatives. Okay, so that was one part of the fundamental theorem of calculus. That was part 2. So that was part 2. Now let's look at part 1. So part 1 says, is sort of the opposite thing. Instead of using antiderivatives to compute an integral, it's saying that the integral itself is an antiderivative. And we're going to think of it more like this, at least in the problems I'm going to show you. Okay, it says that the derivative of an antiderivative, which is this kind of complicated thing, they undo each other, right? So the way I tend to think of this is that derivatives and integrals, are opposite operations. Like one undoes the other. It's not perfectly correct, right? Because you have to format this sort of correctly. Like you do have to have the sort of the variable in the top part for this to be exactly correct. So it's not quite as simple as like saying, addition and subtraction are opposite, because you can subtract off whatever you added. But it is sort of the best version we have for integrals and derivatives. It says derivatives undo integrals. And you can also think of number 2 as saying, integrals undo derivatives, right? So the second one, you could have like an integral from a to b of f prime. An antiderivative of f prime is just f. So this one says integrals undo derivatives. But but you pay the price because you have sort of this subtraction of the antiderivative. But anyway, so that's sort of a side point. But yeah, let's concentrate on this part up here, that the derivative of this integral, they cancel out and you just end up here. Okay, so if somebody asked you a question like this, so given that f of x is the integral from, say, 0 to x of 1 over 2t squared minus 3 dt, what is f prime of x? Right, so we have some function here, this capital F, that takes the area under this 1 over 2t squared minus 3 thing, calculates the area from 0 up to whatever you plug in, right? And, well, this is basically just set up so that it's exactly the fundamental theorem, right? So f prime of x, that's just the derivative of what it is. Which the fundamental theorem of calculus says if you have exactly a constant on the bottom and just x in the top bound, and you take the derivative of it, then it's just exactly plugging in x. So you just take the x and you plug it in for t. Right, because the integral did the antiderivative, then the derivative undid the antiderivative, and so you just ended up back with what was inside originally. They all sort of canceled out. So it's sort of a fancy way of saying that you did something and then undid it. Okay. Okay. Let's make it even a little more complicated. So now we're going to be given a different function. It's going to be 3 to x squared. And let's just put a square here. So now let's again compute. So this upper bound is x squared. So again, we want to compute the derivative here. So that's, that's just saying that the derivative will be the derivative of this integral thing. Oh, what am I writing? dt. And so you might first guess that we can just plug x squared in, right? Or something like that, but it's not quite right. So the essential way you have to think about this is when you have something in one of the bounds that's not just x, if it's some other function of x, like x squared or sine of x or 3x or tangent of 4x or something, then you have added work, because essentially, in this function above, if I substituted x squared in for x, then you would get something like this. So the point is that there's sort of a chain rule going on here. And so to make that more clear, the way I like to think about it, whenever I need to reconvince myself of this, is that, this square root of 2t squared minus 2, I don't know what its derivative is, or its antiderivative is off the top of my head. But, as long as it has an antiderivative, which almost anything you can write down has an antiderivative, unless it has like vertical asymptotes. So let's call like we don't know what the antiderivative is, but we sort of know that it has one. We just don't know what the formula for it is. So I'm just going to give it a name. I'm going to call it G. Okay, and so think back to what, if I covered up the derivative part, and I imagine that part didn't exist, then what we were doing before is said, to calculate this integral, we would find the antiderivative, then we would plug in the top minus the plug in the bottom. Right, so what that means here is that means we would be taking the derivative of the antiderivative of this thing, which is G, then plug in the x squared up. Right, because remember the steps are you find an antiderivative of whatever's in here. That thing was G. Then you plug in the top bound, so I plugged x squared in. Then plug in 3, right? And well, now if you think about this, G is just some function. If I plug 3 into any function, it's just going to give me a number out. So the second derivative of the second part is just 0. But what about the derivative of the first part? Well, this is a composite function, right? It's combined x squared with g of x by plugging one into the other, right? This is a chain rule. Right, so chain rule says here that you would get g prime, but you keep the original inside, and then you get an extra derivative of inside, which is 2x. Okay, so we're almost there. Now, if g is the antiderivative of this inside bit, then what's the derivative of the antiderivative? That just means it's just the square root of 2t squared minus 2. So g prime is, so like g prime of just x would be 2x squared minus 2. And so, sorry, g prime. And so g prime of x squared is used, you have to plug in x squared. Sorry, I should write it out. So now I plug x squared in for x. So I have an x squared squared minus 2 times an additional 2x. Okay, so now if we look back to what actually happened here. So what actually happened here is, well, if we think about the previous problem, so in the very simplest problem, what did we do? When we took the derivative of an integral and we just had x in the upper bound, then we just plugged that x in, right? And we ended up with the function itself. When we have an x squared, or something that isn't just x, we also plug it in, but then we have to multiply by the chain rule. So we do plug in x squared, but then we have to multiply by the derivative of that bound because there's a chain rule. So that can be a simpler way to think of it. Okay, so questions about that one? That one usually tends to confuse a lot of people. Okay. So we're going to do one more. But before we do that, let me give you one to try to make sure you're on the right track. Okay, so give this one a try. If I give you, sorry, I have to put this as an x, 3x to the fourth. So see what you would get if you did this one. I'll give you a minute or two to think about it. Okay, so there's sort of two ways you could have thought about this. So this one was a little bit different in that the bottom bound was the one that involved the x's, right, instead of the top one. So one way of doing this would be to just switch the bounds. But when you do that, you have to add a negative. So you could just put an extra negative and do it just like we did before. Sorry, when we switch it, we get 1 to 3x to the fourth. And so then g prime will be minus the derivative of this. And remember from what we did before, essentially what that means is we plug 3x to the fourth in for, sorry, I should keep all my variables correct. Theta, theta. You plug that in, and then you have to multiply by the derivative. So this is minus tangent of 3 times 3x to the fourth, all inside the tangent, times, from the chain rule, you get 12x cubed. Okay, so that would be one way to do it. The second way, which is more general, and sometimes you need to use that way, as I'll show you in the last problem we're going to do today, is the second way would be, so let me just copy g. G of x was 1 to 3x to the fourth, or no, it was the opposite. Why do I keep... was like this. This was what was given. And we can do it just like we did before. So we can think of this part inside here has some antiderivative. You probably don't know what the antiderivative of tangent is. It's something we haven't talked about. But it has one. I'll call it just capital G. Doesn't really matter what you call it. And so, you know, so this whole thing is just going to be the antiderivative with the top plugged in minus the antiderivative with the bottom plugged in. And then when we take the derivative, we get g prime of x. It's got to be the derivative of this thing. The derivative of g of 1, well, g of 1 is just a number, so it'll be 0 minus, then we have a chain rule here, times 12x cubed. And then we remember that you know, g was the antiderivative of tangent of 3 theta, so the derivative of the antiderivative was just tan of 3 theta, so you would get tan of, you know, 3 theta, but instead of theta, we have to plug in 3x to the 4th times 12x cubed. So you would get the same thing. But yeah, so that's 2 ways of doing that. Let me show you one more that's sort of the most general thing that can happen. So let's just compute this thing. So we have this kind of horrid looking quantity. It says, what's the integral of 1 over t squared from minus sine of x to x cubed plus x squared? We want to know the derivative of that. And so in this case, I think, at least for me, it's the easiest to you know, think of, you know, this interior part has some antiderivative. Maybe I should, which way should the arrow go? So the antiderivative of 1 over t squared is something. We could actually figure it out here, right? This is something we could actually just compute out. But I want to show you, you know, like if I add a plus 1 here, we wouldn't be able to do it. But we actually know that the antiderivative would be minus 1 over t, but I'm just going to call it some name g. And so, you know, this would be the derivative. And then to compute an integral, you take the antiderivative and you plug in the top, minus plugging in the bottom. Okay, and then when you take the derivative of this, you get g prime with the same interior times the chain rule. Minus g prime of minus sine of x times the derivative of minus sine, which is negative cosine of x. So you get this mess. But we know that the derivative of g is just 1 over t squared. So what you would get is this mess. Plug this into 1 over t squared. And then we'd have times 3x squared plus 2x And then in the second one, we'd have 1 over minus sine of x squared times negative cosine x. So you'd get something like this. Okay. And I can tell you an even shorter way to remember it. If you really want a formula to use, sort of the most general formula that always works is, as long as everything makes sense, is if you take the derivative of an integral where you have, let's see, what do I want to use here? Say r of x. So you have some functions in the top and bottom, r of x and s of x, and then you have some function in here. Well, that is, what you always do is you plug in the top. So you take your s of x and you throw it in there. But then you have to multiply by the derivative of s. Right, so that's what happened here is we plugged 3x squared, or x cubed plus x squared, and we plugged that in here. Then we multiplied it by the derivative, right? And then you subtract, doing that same thing with the bottom one. So you plug your bottom bound in, but then you multiply by the derivative of the bottom. And these derivatives, or sorry, this should be an x. These derivatives are why, if you have a constant on one of the bounds, that, the derivative of a constant is 0. So those things don't ever show up, right? So that's why, like, the first examples we did only had one term. Okay. So this is sort of the most general formula, though I tend to just remember it sort of this way up here. Okay, any questions about this so far? Alrighty then, well, that'll be it for today. On Wednesday, we're going to continue on talking about the fundamental theorem of calculus, so we're going to kind of talk about a little bit more of its applied stuff. And remember, you'll have your quiz and your homework due on Wednesday. But other than that, have a great day, and I'll see you on Wednesday.